Hi, in this video, I'm going to be going over how to use ISETBIO to create a ISETBIO scene object, which is a representation of visual stimulus. And in this particular video, we'll focus on a image displayed on a computer monitor, which is, I'd say, the most basic kind of scene we can represent in ISETBIO. In other places, we can tell you more about how we represent full scenes in 3 dimensions and work with those. So to do this, I'm going to share my screen. And get Zoom out of the way here. Nope, I don't want to do that. And I'm in this video, I'm using ISETBIO, and so you need to have the ISETBIO distribution on your Matlab path. And then I am going to be going through a Matlab LiveScript that we designed to illustrate how scenes can be created in ISETBIO, and that's in a separate repository, the ISETBIO LiveScript repository. So here I have the script livescript underscore scene ls_scene for stimulus on display, Matlab LiveScript in my Matlab editor in Matlab, and I've got ISETBIO on my path. I'll note that Nicholas Kateris put this script together. He's a key part of the ISETBIO team and has done much of both the development of the code and also development of the science underlying ISETBIO. So ISETBIO in general works on a series of objects, and each object represents one kind of quantity that we use in modeling the early visual system. And in creating a scene, we're actually going to begin by creating an object which describes a visual display. And I'll say that this LiveScript code is fairly high level, designed to illustrate how, at a high level, we can do things in ISETBIO. You can go down through the code, which I won't do here, and see more about the underlying routines. The other thing I'll comment on is that LiveScripts are really great for illustrating concepts because they allow annotations and images and collection of the output of the code. We have not found them so useful for actual production work, as everything goes a little bit more slowly when you do it in the LiveScript. So first thing that we do to work with an image on a display is actually create a model of a display, and we have a number of displays that have been calibrated and set up that we have for modeling. So here's a single line display create, where this is one of the pre-available displays, an Apple LCD display that was measured and calibrated, and we're going to specify that the observer or subject or person is viewing that from 0.57 meters. So I'll go ahead and execute that line. And then notes here, the key things we care about with respect to a display are the spectral power distribution of the monitor's channels or primaries. And that's how much power is emitted by each channel as a function of wavelength when the channel is at its maximum output. The gamma curve, which describes the relationship between the input values that are provided to the digital frame buffer and how much light actually comes out for a particular primary. And also we could care about summaries of the spectral power distribution, such as the chromaticity coordinates and maximum luminance. And we'll see a little bit later how to get some of that information. In any case, having created the display, we can now get information about it, such as what wavelength did we specify the channel spectral power distributions over. So I could get that. Whoops. Oh, I see, I selected wrong there. Let's see if I can just execute this whole cell here. Great, and it brings up this graph here, which shows you the spectral radiance of each of the 3 monitor channels, the red, green, and blue. And the units of the radiance are watts per radian per meter squared per nanometer. And here they are, and the same graph is shown over here. Now, the display also has gamma functions, and this code here is just a little excerpt from a chapter describing the idea of gamma functions. But basically, we write out digital values into a frame buffer, which we might call capital R, G, and B, and some fraction of each monitor's channel's maximum intensity comes off, which we can note by little r, G, and B. And so that information is contained in the characterization of the display. We can get the gamma table, we can visualize it, and we can compute an inverse gamma table, which will help us go in the other direction from these, which are typically what we want to control, to these, which is what the signals we have to provide when doing video. So I can select this and execute it. And now we've got graphs of the gamma function of this monitor, the forward direction. This was measured at some point by somebody for an Apple LCD monitor. And the inverse gamma functions. They're a little irregular here at the bottom because in this particular monitor, the output at low input values was below threshold for measuring with whatever instrument was used to measure it. Other things we might care about with respect to a monitor, and I won't go through this in great length, are just the basic colorimetric properties represented in standard coordinates. So for example, if I evaluate this, we see a nice display of the chromaticities of the three monitor primaries, along with the gamut triangle that you can produce. These are the chromaticities you could produce in this monitor. Here's a spectrum locus, the chromaticities of monochromatic light, ranging from short all the way around to long in the CIE XY chromaticity diagram. So all of this kind of functionality for examining properties of display is provided within ISETBIO. Now, the display itself doesn't tell us about a stimulus. It's not a full description. And so in ISETBIO, what we want to do is specify what we call a scene, which is a fuller description of a visual stimulus. And in this example here, we'll be going through parameters for an achromatic or isochromatic Gabor patch, sinusoidal grading windowed by a Gaussian, and we're going to realize it first in an abstract form, and then we'll realize it on the display we've set up above. So lots of parameters for Gabors. They've got a spatial frequency here, 10 cycles per degree. They have an orientation. They have a spatial phase. They have a size and degrees of the image. They've got the size of the Gaussian window. We've got the contrast of the sinusoidal grading before it's been windowed. We have the mean luminance that we'd like. And these are now set for empty because we haven't put it on a display, which would be the pixelization of the image. And so we can just define those parameters in a Matlab structure, which I'll do here. And then in order to put it on a display, we better decide how many pixels we want. So we first of all can get from our display the display size, display pixel size in meters. So I'll do that here. They're kind of small in meters, 10 to the 0.1 times 10 to the minus 4, which makes sense for pixels. And then we can get other things like the viewing distance. And from that, we can do a simple calculation to figure out how many pixels we want in order to have the size of the image that we specified above for the stimulus on the display, dividing by the size per pixel to get the number of pixels we need for the width and height of this display. And let's just make sure those are reasonable numbers. 301 by 301 is not a crazy size for something displayed on a monitor. Okay, now having gotten that, we want to generate a Gabor scene. This is a high-level wrapper which takes our stimulus parameters and produces a scene that describes in ISETBIO form that describes that. Scene is a structure in this particular case, and it's got type, it's got data, which are going to be the actual image data. It's got a bit depth. It's got the units of power in photons per second, 31 wavelengths specified in there, and other things. So we've specified the scene, and now we can set the scene that we've created to be at the viewing distance that we wanted, so that matches up. And we can give it a name so we can refer to it later if we want. So we've done all those things. And now we would like to look at that or visualize it in some way. And this is sort of an abstract scene. It's actually, by default, the equal energy spectrum is the achromatic stimulus. We could now think about looking at it where we would get the size of the spatial support in millimeters, get the sRGB image corresponding to the scene. This is just a way to visualize. sRGB is a standardized abstract description of displays and allows us to produce RGB images that are fairly standardized. We could get a map of the CIE tri-stimulus coordinates of the scene, and we can convert to X and Y chromaticity just by doing that little calculation here. Compute the mean luminance. which is just the Y value of the XYZ map, where the default units are candelas per meter squared. And go on to get the mean luminance, the mean chromaticity, and then we could visualize this scene in terms of its sRGB image. And there it is, a very small fraction of a 10 cycle per degree Gabor patch, because the actual size in degrees is quite small. And this is out there in space at the viewing distance. So everything is in physical units. The other thing we might want to do, since this is specified at each wavelength, this is a stimulus out in the world, and therefore really described by its spectral radiance, is to plot the spectral radiance or visualize it in some way. And so here are some ways we do that. Each of these is the plane at one set of sample wavelengths. These aren't all the sample wavelengths that we would use in general, but span much of the visual spectrum here. And because this is an equal energy spectrum, they all look the same. We can see that in this diagram. Now, given the scene object, as we say, that's an abstract thing, but we have a display, and we'd like to put on a display an image that's a point-by-point metamer of the scene that we set up, so that we could characterize what an observer would actually see should they look at this. And realize scene on display is, again, a high-level routine which takes our scene object, our display object, and it produces a scene object which represents the scene as it would be on the display. And we'll look below about how that's a little different from the abstract representation. So I evaluate that, and we can visualize that. Now the displayed scene. And what we can see is that the rendered image looks just the same as we had before. Whoops, where did it go? For the Gabor scene. And that makes sense, because this is a point-by-point metamer for the equal energy spectrum scene that we set up in the abstract. But that the wavelength by wavelength properties are different. So here is the one on the display, which has very little power in the short, and it varies with wavelength. And that's because this scene is a metamer for the equal energy spectrum, and it's a metamer with respect to the monitor phosphors, or monitor primary spectral power distributions. It's a mixture of those, and thus doesn't look flat as a function of wavelength. And that's, again, in the LiveScript, comes out down here. If we wanted, instead of looking at these pictures, to look at actual spectra, we could pick a target location. And then we could plot a slice through that. And this first slice is through the original scene that's an equal energy spectrum, not tied to the particular mixture of primaries on a display. And then if we do the scene on the display, which is here, so now we're doing, instead of the original scene, the displayed scene, do the same basic thing. We see that this, this spectrum here is the spectrum of a particular location on the display, which is a mixture of the three channels, and is different from the equal energy spectrum. But these two lights would be metamers of each other once viewed by the human visual system. Okay, so that's all we really need to do to set up a simple ISETBIO scene with a Gabor patch, and that would allow one to explore how the visual system responded to quite a wide range of stimuli with different spatial properties as defined by the Gabor structure that we set up above. So that's the end of this initial video, and we'll go on in some additional videos to show how, once you have an ISETBIO scene representing something, you can begin to compute how it's processed by the visual system.